Hi there and welcome back. For those of you who are joining first time, I am Hasid Thanki, the founder of presentation series called Intro to Individual Life Underwriting. Let's do this today. Let's review timing and duration of ECG waves, segments and intervals. This is your friend SA node. This is AV node, bundle branch, atrium ventricles that you know. If you remember, we reviewed this galvanometer, or simply speaking electric meter. And there is a pointer that comes out, or the needle, okay, and that needle will go up and down depending upon the electrical events that happens in our heart that generates the cardiac vector. That cardiac vector ultimately forms the ECG patterns. So today we will see the timing, duration of waves, segments and intervals. So let me draw I know this is intro session. Those of you who have carefully seen the ECG paper is a calibrated paper, and if you carefully look at that, it will have a horizontal and vertical lines like this. So you will notice on the ECG tracings that there are heavy horizontal and vertical lines like this. I'm just trying to draw as far as possible, but try to focus on the concept. So on the ECG paper, you will see the horizontal and vertical dark lines like this. Now you remember we talked about the pointer or the needle that goes up and down, and the ECG papers, if connected, moves like this. So this is a special calibrated paper. It moves at a certain speed, and this is like one big square, okay. So this big square, if properly calibrated, the ECG papers, the way it moves, and here there is an ink, so the needle will keep on recording those wave segments and intervals on the ECG paper. If properly calibrated, the typical speed of the ECG paper would be such that in a minute, whatever electrical activity happens in our heart, in 1 minute, the ECG paper, the way it rolls and at the speed, and the needle that it records, it can move 300 big squares like this, the number 1 that reflects here. That big squares So one big box or one big square. Likewise, there can be 300 big squares that can pass through the ECG paper, and the pointer or the ink of the needle would record those events. So, are you with me? Okay, so that means what? We can say that 300 big square, okay, 300 big square equal 1 minute, okay, or we can say that 300 big square equal 60 seconds. So whatever activity happens in the heart, that gets recorded graphically on the ECG paper, and it can move up to, it moves actually 300 big squares. So logically, what would be the duration of one big square? So one big square equal 60 seconds by 300. So if you do the simple math, what it comes to? 0.2 second. So make a note of this, how we are arriving at this number. Simple logic. So one big square equals 0.2 second of time duration. Okay. Now, if you pay close attention to the ECG tracing, you would see that there are likewise small lines within those big squares. So it goes like this. So you will have within the big square such small horizontal as well as vertical lines like this. Okay. So that you understand, I have drawn this for the simplicity here. And likewise, you can have in your entire ECG tracings, but just to simplify the concept, I have just drawn here. You could finish the remainder of the lines. So we were at this equation, one big square equals 60 seconds, which means basically 1 minute, and there are 30 big squares that can pass through given the properly calibrated ECG paper to correlate with the speed of the paper that moves in this direction. So if there are 300 big squares that can move underneath the needle, it boils down to 1 big square equals 0.2 second. So if you carefully notice, within 1 big square there are 5 small square. Okay, so like 1, 2, 3, 4, 5. So 1 big square equal 5 small square. Okay, likewise you could have it same thing horizontal as well as vertical. So let's say in this big box, big square, you have 1, 2, 3, 4, 5. Okay, so 1 big square equals 0.2 second. So can we say that 1 big square equals 5 small square? Okay, so 1 big square equal 5 small square. 1 big square equal 5 small square. Or we can say 5 small square equal 1 big square equal 0.20 second. Okay, so logically if you do the simple math, if we have to figure out 1 small square equal 0.2 second divided by 5, so it comes to 0.04 second. Okay, if you want to succeed in your life underwriting career, this 0.04 second, that means, let me draw it here, that means this much. One small square equals 0.04 second. Simple. Does it make sense? So when you look at the ECG tracing, when you see the small square, it equates to 0.04 second. When you look at the ECG tracing and you see a 1 big square, it equates to 0.20 seconds. Okay. Now remember, you know now P, Q, R, S, T, your alphabet. So let's say we draw the P wave. So P wave represents what? Atrial depolarization. So the time it takes from the depolarization, the SA node gets fired and it reaches up to the AV node. So the duration of the P wave is 2.5 small square. So let me draw that here, that way you will see. So 2.5 square would be like this. So this is the atrial depolarization, and now we know based on our prior sessions that atrial depolarization reflects P wave, right? And then the heart is silent in the AV node, so there will be a isoelectric line we call PR segment. You know now that. So that PR segment again is of another 2.5 on an average, another 2.5 duration, or it takes 2.5 small square. So that would be from here up to here. So 2.5 square, 2.5 small square for the P wave, 2.5 square to small square for the PR segment, right? So now we have the entire PR interval, because PR interval includes PR wave plus PR segment. Okay, so that entire process takes what? How many seconds? 0.20 seconds. Now we know our alphabet. Guess, on an average in a normal heart, typically what would be the duration of next QRS complex or the QRS interval, right? So I'm trying to unfold such that those who are studying this for the first time, they can easily digest, they can easily understand. So you don't need to be a rocket scientist to understand this. First P wave takes 2.5 small square. The isoelectric line called PR segment takes another 2.5 small square. The entire PR interval takes 2.5 plus 2.5, so 5 small square, or as we know, 1 big square. Then follows the QRS complex, likewise 2.5, 2.5, again 2.5. Okay, so the QRS complex takes another 2.5 small square. So let me draw that here. So that would be like now if you add 2.5 for P, 2.5 for PR segment, 2.5 for QRS complex. So how far we are at so far? So that comes to 7.5, right? If you add another 2.5, it comes to 10 small square. Okay, you remember the QT interval that I was talking about? QT interval on an average in a healthy heart, normal heart, it takes 10 small big squares. So the QT interval, as you now know, starts from the beginning of the Q wave. So we are talking about the beginning point of the depolarization of the ventricle all the way up to the end of the repolarization of ventricle. So that would be the point where the T wave ends. So that entire process takes 10 small squares. So let me draw that here. So 2.5 plus 2.5 plus 2.5. And another easier way to know that, to finish the cycle of PQRST, would be the QT interval that takes 10 small squares. So as we know, the QT interval starts from here, and you say 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So typically what happens, your T wave ends here. So the way it goes, PR or the PR segment, QRS, and then this is your ST segment, or the Plato phase of the ventricle cycle. Okay, so does this make sense? It's very simple. So the septal or the major or the basal depolarization of the entire ventricle, plus then the repolarization starts and it ends at the T waves. That is what the entire cycle of the depolarization up to the repolarization, the entire cycle gets reflected via QT interval that you know starts from here up to here. Okay, so that's the QT interval. Okay, now one thing I may want to further simplify, I can say that when you say 2.5, so do the simple math. If one small square equals 0.4, so 2.5, let me write here, 2.5 small square. Do the simple math. So one small square equals 0.04 second, right? So that is for one. Then this is for the other small square. And we are saying 2.5. So it would be the half of this. So 0.02. So basically, when we say 2.5 square, we are saying altogether 0.1 second. So the ventricular depolarization takes 1 second on the ECG tracing. The heart remains silent for another 0.1 second. That is reflected via PR segment. And likewise, you add up the QRS and the entire up to the T wave. So you don't need to be genius about understanding this. You follow step-by-step process and it will make sense to you. Now remember, we are talking about in general normal heart, right? And as we know that electrical events that happens in the heart that forms the cardiac vectors, that cardiac vectors ultimately forms the ECG patterns, the waves, segments and intervals. We are talking about number one basic. We are not talking advanced. These are the fundamentals. That's why I am doing spoon feeding for those of you who are joining the profession. Secondly, we logically need to realize that when there is a pathology, when there is any abnormalities, in abnormal heart, the cardiac vectors generated would be abnormal. As a result, the ECG patterns would be formed are bound to be abnormal. So that would deviate. So you may see instead of 2.5 up to 3, and then the pathology starts. We can get into those details later. Likewise, when you say 10 small square for the QT interval, it may happen instead of 10, it may happen 11. So simple math, simple logic, when we say 10 small square equal, if you do the simple math, it boils down to what? How many seconds? Do the simple math. 0.40 second. Now, you may see once in a while on the ECG tracing that it may go up to 11. So the 11 small square would be what? 0.44 second. It's a simple math. You can do it. Okay? For the beginners, those who are joining and those who are not aware of the basic or the fundamentals, hope this helps. Let's take a small break and then we'll continue again. Okay? Take care. Bye now.